Hello, dreamers and cosmic explorers. Welcome to Hafi Sleep. Whether you're here to drift away into the cosmos or to simply unwind with a truly out-of-this-world thought, I'm so glad you found your way here. Tonight, we're embarking on a journey to the very edge of imagination and physics to ask a question that is as terrifying as it is fascinating. What would happen if we could take the most powerful weapon humanity has ever created and drop it into the most destructive phenomenon in the universe? What if we tried to nuke a black hole? We're going to explore every bizarre possibility. Can we kill a black hole with an atomic bomb? It's a story of ultimate power meeting ultimate inevitability. And it's the perfect way to let your mind wander before it drifts off to sleep. But before we begin our descent into this cosmic mystery, do me a quick favor. If the sound of this adventure is your kind of relaxation, please hit that subscribe button and give this video a like. It truly helps this channel grow and allows me to bring more incredible stories to help you unwind. Also, I love hearing from our wonderful community from all corners of the globe. Let us all know where in the world you are and what time it is for you right now. Are you cozying down for the night in London? Just waking up with the sun in Sydney? Or maybe it's the middle of the afternoon in Toronto and you're just taking a mindful break? Drop a comment below and share your little corner of the planet with us. All right, with that done, just get comfortable. Close your eyes if you'd like, and let your imagination float freely. Let's begin our journey to the heart of a black hole and see what happens when humanity's finest hour meets the universe's ultimate force. So, you're staring up at the night sky, your mind wandering through the infinite dark, and a truly spectacular, gloriously unhinged question pops into your head. Can we blow out a black hole with our most powerful nukes? I mean, really line up the biggest bomb we've ever built. Aim it right at the heart of that cosmic vacuum cleaner and push the big red button. It's the ultimate showdown. The universe's most destructive weapon versus the universe's most destructive phenomenon. It feels like the plot of a blockbuster movie, doesn't it? The plucky human race facing down an existential threat with a gutsy all-or-nothing gamble. Heroes would monologue about human ingenuity. There would be a tense countdown. But the universe, my friend, doesn't care about our blockbuster plots. It follows rules, and when it comes to black holes, those rules are so bizarre, so mind-bendingly absolute, that our cinematic daydreams don't stand a chance. So, let's embark on a thought experiment. Let's take this wild idea and follow it, step by step, possibility by possibility, to its ultimate and perhaps disappointing conclusion. Buckle up, because we're not just going to skim the surface. We're going to dive head first into that black hole of a question, and we're not coming out until we've explored every last cranny. First, we need to understand our combatants. In one corner, we have the nuclear bomb. When we talk about a nuclear bomb being humanity's masterpiece of self-destruction, we are hitting on a profound and terrifying truth. It is, in a very real sense, the final product of our curiosity about the world. It began with philosophers pondering the nature of matter, with chemists and physicists breaking down the world into elements, then atoms, and then the tiny buzzing solar systems of protons, neutrons, and electrons within those atoms. We peered deeper and found that nestled in the heart of that atom was an energy so profound, so deeply woven into the fabric of mass itself, that to unlock it was to change the human condition forever. This isn't just about a big explosion. It's about the moment we learn to tap into the power that binds the universe together. The nuclear bomb is, therefore, a philosophical object as much as a physical one. It represents a point of no return in human history, the moment we gained the power not just to change the course of human events, but to end them altogether. It is the ultimate expression of the double-edged sword of knowledge, a creation that inspires equal parts awe and dread. Now, the key that unlocked this power, as the text rightly points out, is Einstein's legendary equation, E equals mc squared. You've seen it on posters, on t-shirts, in cartoons. It's probably the most famous equation in the world, but what does it really mean? Let's break it down into plain language. The E stands for energy. The M stands for mass, which is essentially the stuff that everything is made of. You, me, the air, stars, everything. The C stands for the speed of light, which is an almost unimaginably fast number, about 186,000 miles per second, or 300,000 kilometers per second. To put that in perspective, a beam of light could travel from the Earth to the Moon and back in about 2.5 seconds. The equation says that this colossal speed of light is squared, meaning it's multiplied by itself. So, c squared is 300,000 times 300,000, which is a staggering 90,000,000,000. That's 90 billion in the units we're using. Why is this number so important? This gigantic number, C2, is the conversion factor. It's the exchange rate between the currency of mass and the currency of energy. Einstein's brilliant realization was that mass and energy are not separate things. They are two different forms of the same thing. Mass is, as he put it, congealed energy. Think of it like water and ice. They look different, they feel different, but they are both fundamentally H2O. In the same way, matter is just a frozen, incredibly concentrated form of energy, and E equals mc squared is the recipe for how to unfreeze it. Because C2 is such an enormous number, a tiny, tiny amount of mass corresponds to a staggering amount of energy. One of the best illustrations of this comes from thinking about a simple, everyday paperclip. If you could somehow transform the entire mass of a single steel paperclip into pure energy, with no mass left behind, the resulting release of energy would be equivalent to the explosion of about 18 kilotons of TNT. That is roughly the size of the bomb that destroyed the city of Hiroshima in 1945. Let that sink in for a moment. The potential energy locked away in the invisible atoms of a paperclip you can hold between your fingers is equal to the explosive force that leveled a city. This is the mind-boggling power that Einstein's equation revealed. On Earth, we can't just convert a paperclip entirely to energy. It requires conditions more extreme than the core of our sun. But in a nuclear weapon, we come heart-stoppingly close. So how do we actually pull this off? How do we convince a tiny bit of matter to give up this incredible energy? We do it by playing with the very core of the atom, its nucleus. There are two main ways we've figured out how to do this: fission and fusion. The first atomic bombs, like the one dropped on Hiroshima, used fission. Fission means to split apart. These bombs use very heavy elements, like a specific type of uranium called uranium-235 or plutonium-239. Imagine the nucleus of one of these atoms as a very wobbly, unstable droplet. If you shoot a tiny particle called a neutron at it, it can cause this droplet to split into two smaller droplets. This is the splitting the atom you hear about. But here's the crucial part. The total mass of those two smaller droplets is ever so slightly less than the mass of the original large nucleus. That tiny bit of mass doesn't just vanish. According to EMC2, it has been converted into a colossal amount of energy, mostly in the form of immense heat and light. Furthermore, when the atom splits, it also spits out a few more neutrons. These neutrons can then go on to hit other uranium or plutonium nuclei, causing them to split and release more energy and more neutrons. This creates a runaway, self-sustaining chain reaction that releases the energy of millions of tons of TNT in less than a millionth of a second. The little boy bomb that fell on Hiroshima contained about 64 kilograms of uranium-235, and only about 1 kilogram of that actually underwent fission. The rest was blown apart before it could react. But that single kilogram of converted mass was enough to release an energy of approximately 15 kilotons of TNT, devastating an entire city. The second type, fusion, is even more powerful and is the principle behind hydrogen bombs, or H-bombs. Fusion means to push together. This is the process that powers our sun and every other star in the universe. In the core of the sun, under crushing pressures and temperatures of millions of degrees, the nuclei of light atoms, like hydrogen, are forced together to form heavier atoms, like helium. Just like in fission, the mass of the resulting helium nucleus is slightly less than the mass of the hydrogen nuclei that went into making it. And again, that little bit of missing mass is transformed directly into the staggering energy that has lit and warmed our planet for billions of years. In a hydrogen bomb, we essentially create a tiny, temporary star on Earth. We use an initial fission bomb explosion, effectively a small atomic bomb, as a trigger. The unimaginable heat and pressure from this fission explosion then slam isotopes of hydrogen, like lithium deuteride, together with such force that they fuse. This fusion process releases even more energy than the fission trigger itself. This is why hydrogen bombs can be made so much more powerful than pure fission bombs. There is no theoretical upper limit to the yield of a fusion bomb, unlike a pure fission bomb, which has practical limits. This two-stage process, fission to ignite fusion, is what allows for the creation of true monsters, the true masterpieces of self-destruction. And this brings us to the star of our show, the absolute king of human-made explosions, the one the text refers to, the Tsar Bomba. Its name translates to King of Bombs, and it was a title well earned. Detonated by the Soviet Union on October 30th, 1961, it remains the most powerful human-made explosion in history. The numbers associated with it are so large, they defy human experience. It was a hydrogen bomb, a three-stage device design that used fission to ignite fusion, and then that fusion energy to ignite an even larger second stage of fusion reactions. The original design had a yield equivalent to 100 million tons of TNT, or 100 megatons. To avoid dangerous levels of radioactive fallout and to give the bomber plane a chance to escape, this yield was reduced by replacing a uranium tamper with one made of lead. Even in this neutered form, its yield was an almost incomprehensible 50 megatons of TNT. To put that in perspective, that is 3,333 times more powerful than the little boy bomb dropped on Hiroshima. It was 10 times more powerful than all the conventional explosives used in World War II combined, including the 2 atomic bombs. The bomb itself was colossal, weighing 27 metric tons and measuring about 8 meters long and 2 meters in diameter. It was so large it barely fit inside a specially modified Tu-95V bomber, which had to have its bomb bay doors removed. The detonation itself was an event of biblical proportions. It was dropped over the Novaya Zemlya archipelago in the Arctic Ocean. The bomb was slowed by a giant parachute to give the bomber and its accompanying observation plane time to fly about 45 kilometers away. When it detonated at an altitude of 4 kilometers, the resulting fireball, a man These neutrons can then go on to hit other uranium or plutonium nuclei, causing them to split and release more energy and more neutrons. This creates a runaway, self-sustaining chain reaction that releases the energy of millions of tons of TNT in less than a millionth of a second. The little boy bomb that fell on Hiroshima contained about 64 kilograms of uranium-235, and only about 1 kilogram of that actually underwent fission. The rest was blown apart before it could react. But that single kilogram of converted mass was enough to release an energy of approximately 15 kilotons of TNT, devastating an entire city. The second type, fusion, is even more powerful and is the principle behind hydrogen bombs, or H-bombs. Fusion means to push together. This is the process that powers our sun and every other star in the universe. In the core of the sun, under crushing pressures and temperatures of millions of degrees, the nuclei of light atoms, like hydrogen, are forced together to form heavier atoms, like helium. Just like in fission, the mass of the resulting helium nucleus is slightly less than the mass of the hydrogen nuclei that went into making it. And again, that little bit of missing mass is transformed directly into the staggering energy that has lit and warmed our planet for billions of years. In a hydrogen bomb, we essentially create a tiny, temporary star on Earth. We use an initial fission bomb explosion, effectively a small atomic bomb, as a trigger. The unimaginable heat and pressure from this fission explosion then slam isotopes of hydrogen, like lithium deuteride, together with such force that they fuse. This fusion process releases even more energy than the fission trigger itself. This is why hydrogen bombs can be made so much more powerful than pure fission bombs. There is no theoretical upper limit to the yield of a fusion bomb, unlike a pure fission bomb, which has practical limits. This two-stage process, fission to ignite fusion, is what allows for the creation of true monsters, the true masterpieces of self-destruction. And this brings us to the star of our show, the absolute king of human-made explosions, the one the text refers to, the Tsar Bomba. Its name translates to King of Bombs, and it was a title well earned. Detonated by the Soviet Union on October 30th, 1961, it remains the most powerful human-made explosion in history. The numbers associated with it are so large they defy human experience. It was a hydrogen bomb, a three-stage device design that used fission to ignite fusion, and then that fusion energy to ignite an even larger second stage of fusion reactions. The original design had a yield equivalent to 100 million tons of TNT, or 100 megatons. To avoid dangerous levels of radioactive fallout and to give the bomber plane a chance to escape, this yield was reduced by replacing a uranium tamper with one made of lead. Even in this neutered form, its yield was an almost incomprehensible 50 megatons of TNT. To put that in perspective, that is 3,333 times more powerful than the little boy bomb dropped on Hiroshima. It was 10 times more powerful than all the conventional explosives used in World War II combined, including the 2 atomic bombs. The bomb itself was colossal, weighing 27 metric tons and measuring about 8 meters long and 2 meters in diameter. It was so large it barely fit inside a specially modified Tu-95V bomber, which had to have its bomb bay doors removed. The detonation itself was an event of biblical proportions. It was dropped over the Novaya Zemlya archipelago in the Arctic Ocean. The bomb was slowed by a giant parachute to give the bomber and its accompanying observation plane time to fly about 45 kilometers away. When it detonated at an altitude of 4 kilometers, the resulting fireball, a man-made star, was about 8 kilometers in diameter. It was visible from over 1,000 kilometers away. The heat from the explosion was so intense that it could have caused third-degree burns to anyone exposed to it over 100 kilometers away. The shock wave it generated was powerful enough to circumnavigate the Earth, not once, not twice, but 3 times. And as the text so vividly describes, it shattered windows hundreds of miles away. In fact, windows were broken in villages in Norway and Finland, over 900 kilometers away. A seismic shock was recorded nearly across the globe. The mushroom cloud climbed to a height of about 67 kilometers, punching well into the mesosphere. The pilot who released the bomb, Major Andrei Durnovtsev, was promoted on the spot, but he also knew that his plane, even at that distance, was not safe. The shock wave caught up to the bomber and observation plane, causing them to drop about 1 kilometer in altitude before the pilots could regain control. Every person involved in the test knew they were witnessing something that transcended weaponry. They were witnessing a fundamental force of nature being unleashed in a single, blinding flash. The Tsar Bomba was not a practical weapon. It was a statement. It was the ultimate flex of nuclear muscle, a demonstration that humanity now held a power that could, in a single instant, unleash a fury that rivaled natural cataclysms. Now, the evolution of these weapons didn't stop with the Tsar Bomba. Scientists and engineers developed something called the yield-to-weight ratio, which measures how much explosive punch you can pack per kilogram of bomb mass. The Tsar Bomba was incredibly powerful, but it was also incredibly heavy. Modern nuclear warheads are marvels of miniaturization and efficiency. For example, the W-88 warhead, which can be mounted on a Trident II submarine-launched missile, has a yield of about 475 kilotons. That's nearly half a megaton. It weighs only a fraction of what the Tsar Bomba did, meaning its yield-to-weight ratio is far superior. The most efficient U.S. weapon ever designed was the B-41, Mk-41 thermonuclear bomb, which had a yield of 25 megatons and a yield-to-weight ratio of 5.1 kilotons per kilogram of bomb mass, a record that still stands. This constant refinement shows that the masterpiece is not a static artifact. It is a continually evolving field of technology, pushing the boundaries of how to most efficiently convert matter into pure, unadulterated destructive energy. And in the other corner we have the black hole. This isn't just a star that died. This is a star that died, collapsed under its own weight, and tore a hole in the very fabric of space-time itself. It's not an object in space the way a planet or a star is. It's a region of space where gravity has become so overwhelmingly powerful that nothing, not even light, not even a single photon, can escape its grip. The boundary around it, the point of no return, is called the event horizon. Think of it not as a physical surface you can touch, but like a one-way waterfall in space. You can paddle peacefully above the waterfall, but once you cross the edge, the current becomes irresistible. There's no swimming back up. That's the event horizon. Inside it, the rules of the universe as we know them break down. Matter is thought to be crushed into an infinitely dense point called a singularity, a place where our current laws of physics simply give up and start crying in a corner. Now, to make this showdown fair, or at least comprehensible, we need to pick our black hole. They come in different sizes. There are stellar mass black holes, the ghosts of massive stars, weighing a few times more than our sun. If we replaced our sun with a stellar mass black hole of the same weight, the Earth and all the planets would continue to orbit it, because the gravity would be the same. It's the density that's the problem, not the mass at a distance. Then there are supermassive black holes, the real monsters that lurk at the centers of galaxies, including our own Milky Way. Our local supermassive behemoth is called Sagittarius A star, and it has the mass of 4 million suns squeezed into a region of space that could comfortably fit inside the orbit of Mercury. The scale is just incomprehensible. For our little experiment, let's start with a stellar mass black hole. It's a more manageable opponent, or so we might naively think. Let's place it a safe distance away from Earth, say, out past Pluto, so we can observe the results without immediately being turned into spaghetti. So, picture the scene, the inky blackness of space, punctuated by distant, untwinkling stars. And there, in the center of our view, is nothing. A perfect sphere of blackness, so dark it's like a hole punched out of the universe. It's not emitting any light, but we might see the ghostly glow of its accretion disk if any nearby gas or dust is being pulled into it, heated to millions of degrees as it spirals down the drain. And we, in our imaginary, impossibly advanced spaceship, are positioning our delivery system. Let's say it's a massive warhead, 1,000 times more powerful than the Tsar Bomba, because why think small? We've mounted it on a rocket, we've aimed it with perfect precision, and with a final dramatic deep breath from mission control, we fire. The rocket streaks through the void. Minutes, then hours pass. It closes in on the black hole. The tension is unbearable. Finally, it reaches the designated detonation point. We send the signal, and boom. From our warhead, a new star is born. A sphere of pure incandescent fury erupts, expanding outward at incredible speed. For a fraction of a second, it is the brightest thing in the solar system, outshining the sun itself. It is a fireball of X-rays, gamma rays, and superheated plasma, a testament to the power locked within the atom. We watch, breathless, waiting for the shockwave to hit the black hole, waiting for a flash, a shudder, a sign that we've made an impact. And we wait, and nothing happens. The fireball expands, and then something very strange starts to occur. The side of the fireball closest to the black hole begins to stretch and distort. The brilliant, perfect sphere starts to look like a teardrop pulled towards the point of nothingness. The light itself, the very energy of our explosion, is being bent. You see, a black hole's gravity is so intense that it warps the space around it. Imagine space-time as a taut, rubber sheet. A planet makes a gentle dip in the sheet. A star makes a deeper well. A black hole is like a weight so heavy it punches a bottomless hole in the sheet. Anything that comes near, matter, light, energy, starts to slide down that slope. Our nuclear explosion is no exception. It's not a solid object, but it is made of energy and particles, and all of it is subject to gravity. The gamma rays, which are just high-energy light, follow the curved paths of this warped space. The particles of plasma are pulled inexorably towards the event horizon. Within seconds, the entire magnificent star-hot fireball is being siphoned, drawn and quartered by gravity, into a swirling, spiraling pattern. It's not hitting the black hole like a bomb hitting a castle wall. It's being accreted. It's becoming fuel. The black hole is simply eating our bomb. The energy from the explosion isn't being released on the black hole. It's being added to the black hole. According to the great Albert Einstein, energy and mass are two sides of the same coin. The colossal energy of our nuclear blast has mass, a tiny, tiny amount, but mass nonetheless. As that energy crosses the event horizon, it actually adds to the total mass of the black hole. We haven't hurt it. We've fed it. We've just made it ever so slightly bigger, ever so slightly more massive. It's the cosmic equivalent of trying to put out a house fire by throwing a stick of dynamite into it. But wait, you might say. That's not fair. The explosion happened outside the event horizon. Surely the force of the blast, the pressure, the radiation should push back against the black hole's gravity. It's a good thought. In a normal environment, it would. If you set off a nuke near an asteroid, the radiation and shock wave would vaporize and push the asteroid away. But a black hole's gravity near its event horizon is something else entirely. For a stellar mass black hole, the gravity at the event horizon is so ferociously strong that the force required to push something away from it, what scientists call the escape velocity, exceeds the speed of light. Since nothing can travel faster than light, nothing can push back hard enough to escape. The outward pressure from our nuclear fireball is like you trying to blow against a hurricane. The hurricane doesn't even notice your puff of air. It just sweeps it up and incorporates it into its own immense power. So, our first, most direct attempt is a spectacular failure. We've learned our first major lesson. You cannot fight a black hole with brute force from the outside. Its gravity is a one-way street that leads only inward. But maybe we're not being clever enough. Maybe we need to change our tactics. What if we didn't detonate the bomb near the black hole, but tried to send it inside? This is the classic sci-fi trope, right? Fly a ship into the heart of the beast and detonate from within. Surely, if we could get a bomb past the event horizon and set it off at the very center, at the singularity itself, we could disrupt it, shatter it, unmake it from the inside out. Let's follow that thread. Imagine we have a magical, indestructible probe that can survive the journey. We load it with our super nuke and program it to detonate the moment it reaches the singularity. We launch it. It crosses the event horizon. From our perspective outside, watching with our telescopes, something very weird happens. Because of the extreme time dilation effects predicted by Einstein's theory of relativity, time itself slows down for anything close to a massive gravitational field. For our probe, as it gets closer and closer to the event horizon, from our point of view, it appears to slow down. It doesn't just slow down, it appears to freeze completely. It becomes redder and redder as the light struggling to escape loses energy until it fades from view entirely. From our external clock, the probe never actually reaches the event horizon. It just smears itself across time, taking an infinite amount of time to cross from our perspective. But let's ignore our perspective and follow the probe's. From its point of view, it crosses the event horizon just fine. There's no wall, no barrier, no dramatic moment. Space is so warped that all paths, no matter which direction the probe tries to move, now lead inward toward the singularity. It's like being in a river that's flowing faster and faster toward a waterfall. You can paddle as hard as you want upstream, but the current is taking you where it wants to go. Inside the event horizon, space and time swap their roles. Outside, you can move freely in space, but are always carried forward in time. Inside, moving forward in time necessarily means moving closer to the singularity. It's no longer a place you can be. It's a moment in your future. So our probe is now inexorably falling toward the center. The tidal forces, the difference in gravity between your head and your feet, are becoming astronomical. This is the process of spaghettification. The part of the probe closer to the singularity is pulled much more strongly than the part farther away. The entire structure is stretched into a long, thin stream of atoms. Long before it reaches the fabled singularity, our probe and our carefully packaged nuke would be torn apart into its constituent subatomic particles. It wouldn't be a bomb anymore. It would be a stream of quark gluon plasma. But let's grant our probe one more miracle. Let's say it survives spaghettification. It arrives at the singularity. This is the point of infinite density, where the known laws of physics cease to exist. Our understanding of gravity, described by general relativity, says that all the matter that ever fell into the black hole is crushed into a point with zero volume. This is, most physicists agree, a sign that our theory is incomplete. At such scales, we need a theory of quantum gravity, which we don't yet have. So, what happens when our nuke detonates at this point of infinite density? The honest answer is, we don't know. It's like asking what happens before the Big Bang. Our science doesn't have the tools to answer. However, we can speculate based on some ideas. One possibility is that the singularity isn't a point, but a ring due to the black hole's rotation, and our probe might, through some mind-bending physics, exit our universe entirely and pop out into another one or somewhere else in ours. This is the wormhole idea, but it's highly speculative and requires exotic matter with negative energy to hold it open, which our nuke certainly is not. Another idea is that the immense energy of the nuclear explosion, unleashed at the singularity, might somehow disrupt the fabric of that infinitely dense point. But here's the problem. The singularity isn't a thing sitting in space. It is the black hole. The entire black hole, from the event horizon inward, is defined by the presence of that singularity. The mass and energy of our nuke, once it crosses the event horizon, is already part of the singularity. The explosion would just be adding a tiny bit more energy to an already infinite density. It would be like trying to extinguish the sun by throwing a single extra hot match into it. The scale is just too different. The singularity, by definition, is the end of the line. There is no disrupting it with more energy, because all energy is already destined to become part of it. So the internal attack seems futile. It's either physically impossible from our perspective, or it ends with our bomb becoming a mere addition to the very thing we're trying to destroy. The black hole, it seems, is immune to our puny human weapons. But perhaps we're thinking about the type of damage all wrong. A nuclear bomb is about releasing energy. What if the key isn't energy, but information? This might sound strange, but bear with me. One of the biggest puzzles in modern physics is the black hole information paradox. It stems from the fact that if you throw something into a black hole, it seems to be lost forever. All the information about what that thing was made of, its structure, its properties, is seemingly erased from the universe when the black hole eventually evaporates, a process we'll get to in a moment. This violates a fundamental principle of quantum mechanics, which says that information can never be truly destroyed. So, we've arrived at one of the most beautiful, mind-bending concepts in all of modern physics. The idea that black holes aren't the eternal, perfect prisons we once thought they were. They leak. They evaporate. They have a life cycle. And this revelation came from a mind that refused to be constrained by the limits of his own body, the great Stephen Hawking. Now, to truly appreciate the sheer brilliance of Hawking radiation, we have to first understand the state of physics before he came along. For decades, the classical view of a black hole, based on Einstein's theory of general relativity, was absolute and grim. It was a one-way street to oblivion. The event horizon was the ultimate point of no return, a boundary from which nothing, not a single shred of information or a flicker of light, could ever escape. It was a cosmic dead end. The black hole could only grow, only get more massive by devouring everything that crossed its path. It was the universe's ultimate glutton, a bottomless pit that forever took and never gave back. This was a clean, powerful idea, but it created a few massive problems for the other great pillar of physics, quantum mechanics. It was as if the universe had two sets of rule books, and they were completely at odds with each other when it came to black holes. Hawking's genius was in trying to reconcile these two rule books. He asked a deceptively simple question. What happens when you take the weird, fuzzy rules of the quantum world and apply them to the brutal geometric gravity of a black hole? The answer he found was shocking. He discovered that black holes aren't black. They glow. They have a temperature. They are, in a sense, warm. This was the opposite of everything we thought we knew. And the mechanism for this is so strange, it forces us to reimagine the very nature of empty space itself. To get our heads around this, we have to start with that seething foam the text mentions. We have to talk about what nothing really is. When you and I look at empty space, say the vast dark void between stars, we think of it as truly empty, a perfect vacuum, a pure nothingness. But according to quantum mechanics, the universe abhors a true vacuum. What we perceive as empty is, in fact, a frenetic, bubbling, chaotic sea of activity. This isn't just a theoretical idea. Its effects are real and measurable. So, what is this activity? The text calls it virtual particles, and that's a great name for them, but let's really unpack what that means. Imagine the fabric of space-time as a vast, calm ocean. Now look closely at the surface of that ocean. On a very still day, it might look perfectly flat and smooth, but if you could look at the microscopic level, you'd see that it's actually constantly jiggling and vibrating. Tiny ripples and waves are forming and disappearing all the time. Now, scale that idea up to the universe. The quantum vacuum is like that ocean surface. It is never still. Because of a fundamental quantum principle called the Heisenberg uncertainty principle, which essentially says that on very small scales, you can't have perfect knowledge of certain pairs of properties, like energy and time. This isn't a limitation of our measuring equipment. It's a fundamental feature of the universe. It means that for incredibly brief moments, energy can simply appear out of nowhere, so long as it disappears again quickly enough to not violate the average energy balance of the universe. This borrowed energy manifests as pairs of particles spontaneously popping into existence everywhere all the time throughout all of space. These are the virtual particles. They are called virtual because they are fleeting ghosts, borrowing energy from the universe and promising to pay it back almost instantly. They always appear in particle-antiparticle pairs, a particle and its opposite counterpart, like an electron and a positron, or a quark and an antiquark, matter and antimatter born together from the energy of the vacuum. And as soon as they appear, they are destined to annihilate each other, colliding and converting back into the energy they borrowed, vanishing without a trace. This entire drama, creation, brief existence, and annihilation, happens in a time span so short it makes a nanosecond look like an eternity. This isn't just a wild theory, it's a well-established part of quantum field theory, and we even have experimental evidence for its effects, such as the Casimir effect, where two metal plates placed very close together in a vacuum are gently pushed together by the pressure of these virtual particles popping in and out of existence outside the plates compared to the space between them. So, picture this. every single cubic centimeter of the space around you, the air in this room, the void between the stars, is a raging storm of these virtual particle pairs flickering in and out of reality. Trillions upon trillions of them every second. It's the universe's background static, a cosmic fizz that is usually completely invisible to us because it all happens in perfect balance. For every particle pair that winks into existence, it winks out just as fast. The books are balanced. The energy loan is repaid. Now let's bring our black hole into the picture. Let's place this constant frenetic dance of virtual particles right at the edge of the event horizon, the point of no return. This is where the magic happens. Normally, a virtual particle pair appears and annihilates so quickly that they might as well have never existed. But at the event horizon, the gravitational pull is so unimaginably strong that it can violently interrupt this delicate dance. Imagine a virtual particle pair popping into existence right at the precipice. One particle of the pair might appear just on the outside of the event horizon, while its partner appears just on the inside. They are born, but now they are separated by the most formidable border in the universe. The particle that is outside, if it has the right trajectory and velocity, might escape the black hole's gravitational clutches. It's like being born on the very edge of a waterfall and getting a lucky kick that sends you flying back to safety. But its twin, the one that was born inside the event horizon, is doomed. There are no paths that lead outward. All directions point inward toward the singularity. That inner particle is irretrievably lost, falling down the gravitational well. This is the key moment. The two virtual particles can no longer annihilate each other. Their cosmic debt, the energy they borrowed to exist, can never be repaid in the usual way. The escaped particle, now separated forever from its partner, becomes a real particle. It is no longer virtual. It's a genuine particle with real energy, and it flies off into the universe. But what about the energy debt? The universe demands its energy back. Here's Hawking's brilliant insight. The energy to make that escaped particle real, to cover its debt, comes from the black hole itself. The particle that fell in isn't just a normal particle with positive energy. In the intricate accounting of quantum mechanics, from the perspective of the black hole and the curved space around it, the infalling particle has negative energy. Now, negative energy is a strange concept. We can't hold it in our hands. But think of it like this. If you have a bank account and you add a negative amount of money, you're actually taking money out. In the same way, when this negative energy particle falls into the black hole, it doesn't add to the black hole's mass energy. It subtracts from it. It's like the black hole has accidentally eaten a piece of antimatter that cancels out a tiny bit of its own mass. So the sequence of events is this. 1. A virtual particle pair pops into existence at the event horizon. 2. The pair is split, one falling in with negative energy, the other escaping with positive energy. 3. The escaped particle becomes real, and to balance the books, the black hole loses a tiny, tiny amount of mass equivalent to the energy of the escaped particle. From a distance, an observer would see a very faint stream of particles slowly trickling away from the black hole. This is Hawking radiation. It's a slow, slow process, incredibly slow. For a black hole with the mass of our sun, the temperature of this Hawking radiation is about a millionth of a degree above absolute zero, which is far, far colder than the cosmic microwave background radiation that fills the universe. That means for such a black hole, it is actually absorbing more energy from the space around it than it is emitting through Hawking radiation. It's on a net gain. It won't even universe expands and cools down much, much more. The timescale for a solar mass black hole to evaporate is about 10 to power 67 years, a 1 followed by 67 zeros. That is so long, it's meaningless to the human mind. It's many orders of magnitude longer than the current age of the universe. But here's the fascinating part. The process accelerates. As the black hole loses mass, it gets smaller. And as it gets smaller, its event horizon shrinks, and its gravity at the surface becomes even more intense, which makes the Hawking radiation process more efficient. The temperature of the radiation goes up as the black hole gets smaller. So, it starts evaporating faster and faster. In the final moments of its life, when it has shrunk to the mass of a large mountain, its temperature would be measured in millions of degrees, and it would be glowing brilliantly. The final stage is a theoretical, colossal burst of energy, a last, desperate release of all its remaining mass in a fraction of a second. It would be a titanic explosion, the opposite of its birth, a final shout as it vanishes from existence. This beautiful, elegant idea solved one problem but created another, perhaps even deeper one: the black hole information paradox. If a black hole evaporates completely, what happens to all the information about the stuff that fell into it? Did it just disappear from the universe forever? Quantum mechanics says that can't happen. Information must be preserved. This paradox is one of the hottest topics in theoretical physics today, a lasting legacy of Hawking's revolutionary thought that started with a simple seething foam at the edge of forever. Now, could our nuclear bomb accelerate this process? Could we use the bomb not to blow the black hole up, but to make it evaporate faster? Let's see. Hawking radiation is an incredibly slow process. For a stellar mass black hole, the temperature of the radiation is far colder than the background temperature of the universe. It's actually absorbing more energy from the cosmic microwave background radiation than it's emitting. It would take longer than the current age of the universe for it to even start losing mass significantly. The time scale for a black hole the mass of our sun to evaporate is about 10 to power 67 years, a number so vast it has no meaning in human terms. When we set off our nuke, we are dumping a massive number of high-energy particles and radiation onto the black hole. Most of it falls in, as we've established. But some of the radiation, the part that doesn't cross the event horizon, could theoretically interact with the Hawking radiation process. However, the energy we're adding by feeding it is vastly greater than the paltry amount it's losing through Hawking radiation. We are, again, making it bigger and more massive. A more massive black hole has a lower temperature and evaporates even more slowly. So paradoxically, by nuking it, we are actually extending its life, not shortening it. We are throwing logs on a fire that's only supposed to have a few embers, making it burn hotter and longer, not putting it out. This leads us to a fascinating and counterintuitive realization. The only way to beat a black hole with a nuclear weapon is to not use it at all. If we could somehow magically convert the entire mass energy of our nuclear bomb directly into Hawking radiation and beam it away, it would be more effective. But that's not how bombs work. They release energy indiscriminately, and near a black hole, that energy is just more food. Let's scale up the problem. We've been picking on a modest stellar mass black hole. What if our target is the supermassive black hole at the center of our galaxy, Sagittarius A star? Its event horizon is millions of kilometers wide. Our entire solar system could fit inside it with room to spare. our nuclear bomb, even our thousand-fold Tsar Bomba, would be less than a firecracker next to this Leviathan. The energy released would be utterly negligible compared to the titanic forces already at play. Supermassive black holes often have colossal accretion disks, with gas and dust swirling at near light speed, generating temperatures of millions of degrees and powerful magnetic fields and jets of radiation that shoot out for thousands of light years. Our nuclear explosion would be a tiny, momentary flicker, instantly swallowed by the ongoing cosmic storm. It would be like trying to alter the course of a hurricane by lighting a single match in the middle of it. Perhaps we need to think even bigger. What if we could build a bomb not out of uranium or plutonium, but out of antimatter? Antimatter is the ultimate fuel. When it contacts normal matter, they annihilate each other completely, converting 100% of their mass into energy, unlike nuclear fission or fusion, which only converts a small fraction. A matter-antimatter bomb would be orders of magnitude more powerful than a nuclear bomb. So, we build our ultimate weapon, a bomb with the mass of, say, Mount Everest, made of pure antimatter. We hurl it at our stellar mass black hole. The resulting annihilation would be a flash of energy so bright it could be seen across the galaxy. Surely this would do something. The result, I'm afraid, is the same. The flash of gamma rays and other energy, spectacular as it is still just light and energy. It is still subject to gravity. The warped space-time around the black hole would bend this incredible flash, siphoning the vast majority of its energy across the event horizon. The mass energy of the antimatter and the matter it annihilated with would be added to the black hole. We might have created a slightly larger flash from our perspective, but from the black hole's perspective, it was just a slightly more energetic snack. The fundamental problem remains. You cannot push with light or energy against a gravitational field so strong that the escape velocity is greater than the speed of light. The energy has nowhere to go but in. What if we could engineer the explosion to be perfectly symmetrical? A shaped charge on a cosmic scale, focusing all its energy onto a single, infinitesimal point on the event horizon. Again, it doesn't matter. The event horizon isn't a physical barrier, it's a mathematical boundary in space. Focusing energy onto it is like focusing the light of 1,000 suns onto the concept of the edge of a cliff. It doesn't make the cliff any less of an edge. The geometry of space-time inside the horizon ensures that all motion leads to the center. At this point, you might be feeling a little disappointed. The black hole seems like a cheat code in the universe, an unbeatable boss. And in a way, it is, within the classical framework of general relativity. But our understanding of the universe is evolving, and theoretical physics has a few more cards to play, concepts that are even stranger than black holes themselves. One such idea is the notion of a naked singularity. A classical black hole, as we've been discussing, has its singularity safely hidden behind the event horizon. The event horizon protects the rest of the universe from the infinite, physics-breaking weirdness of the singularity. This is called cosmic censorship, the idea that the universe doesn't allow naked singularities to exist. But what if we could blow away the event horizon? If we could somehow remove the mass and energy that creates the event horizon, we would be left with a naked singularity, an infinitely dense point exposed to the universe with no event horizon to shield us from its wrath. What would that be like? We have no idea. The laws of physics as we know them would break down completely in its presence. Cause and effect could become meaningless. It might be a gateway to other universes, or a source of infinite energy, or an unpredictable font of new physical laws. It would be the most terrifying and wondrous object in existence. So, could a nuclear bomb create a naked singularity? Theoretically, if you could remove enough mass from the black hole fast enough, you could lower its mass to a point where the event horizon would shrink and vanish, exposing the singularity. But how do you remove mass? By adding energy? No, that adds mass. You need to make the black hole lose mass. We've already talked about Hawking radiation, but that's far too slow. Another theoretical idea is the Penrose process, which involves stealing energy from a rotating black hole's ergosphere, a region just outside the event horizon, where space itself is dragged around at near light speed. It's a complex and theoretical idea, but it involves sending in an object that splits in two, with one part falling in and the other escaping with more energy than it came in with. Could a nuclear explosion be engineered to perform a Penrose process on a massive scale? It seems incredibly unlikely. The precision and control required are far beyond the chaotic, explosive nature of a bomb. The bomb's energy would be far more likely to be absorbed than to be cleverly harnessed to extract rotational energy. It's like trying to perform delicate brain surgery with a sledgehammer. Perhaps the only way a nuclear bomb could affect a black hole is not through direct action, but through a chain reaction. What if the black hole was not in a vacuum, but was in the center of a star or a galaxy? Could we use the bomb to trigger a larger event that would then affect the black hole? For instance, if a black hole was accreting matter from a companion star, could we use a nuke to disrupt the flow of matter, perhaps pushing the star away or altering its orbit, thereby starving the black hole of its fuel source? This is a more subtle approach. We're not attacking the black hole itself, but its environment. In this scenario, a sufficiently powerful explosion, placed at just the right point in the complex gravitational dance between the star and the black hole, could potentially alter the dynamics. It might push a stream of accreting gas just enough that it misses the event horizon, or it could change the star's orbit, making it more elliptical. This wouldn't destroy the black hole, but it could put it on a diet, making it less active, dimming its accretion disk. This is probably the most realistic, albeit still fantastically difficult, way we could affect a black hole with a bomb. We'd be a cosmic pest, a mosquito buzzing around a giant, trying to divert its food supply rather than trying to kill the giant itself. Let's take a moment to consider the reverse scenario. What if a black hole wandered into our solar system and we decided to nuke it to deflect it, to push it away from a collision course with Earth? This is a common trope in disaster movies. Blow up the asteroid to save the world. Would it work for a black hole? The answer is a resounding no, for all the reasons we've already discussed. A black hole's gravity is a function of its mass. To deflect it, you need to apply a force to it, to change its velocity. But to apply a force, something has to push against it. When our nuke goes off, the expanding shell of debris and radiation would push against anything in its path. But if that path includes a black hole, the push is ineffective. The energy and particles that would normally provide the thrust are simply captured by the black hole's gravity and fall in. There's no recoil, no push. The black hole would continue on its path, utterly unfazed, perhaps having gained a minuscule, immeasurably small amount of mass. It would be like trying to push a bowling ball by throwing feathers at it. The feathers just don't have the oomph to move it, and most of them just land on it and add to its weight. This thought experiment has taken us from a dramatic cinematic explosion to the quiet, inexorable laws of gravity and quantum mechanics. We've moved from brute force to subtle information theory. And what have we found? That our mightiest weapons are like pea shooters against a galactic titan. The black hole, in its silent dark majesty, is a testament to the fact that the universe operates on a scale of power and time that dwarfs human imagination. We are temporary creatures in a cosmos of ancient, enduring phenomena. But this isn't a story of defeat, it's a story of awe. The fact that we can even ask this question and follow the logic of physics to its conclusion is a triumph of the human mind. We can't nuke a black hole, but we can understand why we can't. We can use mathematics and observation to peer into the heart of these cosmic mysteries. Our weapons may be insignificant, but our curiosity is not. The black hole wins the battle of brute force, but in understanding it, we win a small victory for knowledge. So, the next time you look up at the night sky and that wild question crosses your mind, what if we nuked a black hole? You'll know the answer. You'll know about event horizons and singularities, about Hawking radiation and spaghettification, about the futility of pushing against a gravitational waterfall. You'll know that the universe is far stranger, far more resilient, and far more wonderful than any science fiction plot. And in that knowledge, you'll find a sense of wonder that no explosion, no matter how powerful, could ever hope to match. The true power lies not in destruction, but in understanding. And that is a far more compelling ending to our story. Good night. Have a deep, calm sleep.